There we go. For the folks at home as well, we have a formative assessment that is due tomorrow. So it's over CFA, so you can do all of it. Just want to make sure that everybody is feeling good enough to be able to analyze their own data because homework 3 based on do it yourself CFA is due next week. So I haven't entertained a lot of conversations with y'all about this, which means either you haven't started yet or you know exactly what you're doing. It's one of the two. So I won't guess as to which one that might be, but just if you are going through your analyses and you hit the point where you're not sure what is a logical thing to do next, let me know. Um, the first drafts of homework 3 need to be at least 3/4 complete for me to accept them. So that means that they don't have to be all the way there. We can have a conversation. You can leave questions for me, in the comments if you're not sure what to do or you weren't sure how to find something. 3/4 of the way there is a solid effort. I had to put that policy into place many years ago when people actually handed me a blank piece of paper and said, "This is my first draft." Realized that I had to be a little more specific as to what a draft would entail. So 3/4 is my, in terms of efforts towards all the points. And just like for homework 1, I will tell you what you need to fix, if anything, and you can fix it during a revision and get all your points back. So it doesn't have to be perfect, doesn't even have to be all the way done, just has to be a nice solid effort to get us there. So even if you know that your data do not lend themselves to CFA, so for instance, some of you may have binary items, go ahead and fit a CFA model to them anyway. And you can see why it is the case that it may not be appropriate in terms of the results with respect to the predicted outcomes for factor scores and things like that. So even if you know that CFA isn't a good choice, I want you to have practice doing it. And then you'll have something to compare to when we get to the IRT IFA stuff that we're starting today. So please finish formative assessment and icon today or tomorrow. We'll go over that on Thursday and then homework next week. And then we have a bit of a breather where we're back to our regular schedule, hopefully enough, if I can keep us on track. All right. Any questions or logistical things that you want to talk about before we dive into some new stuff? All right, let me get the chat window open just in case anybody, oh, it won't, there it goes, just in case anyone wants to chat with me. All right, so are you excited? Some new stuff? You got to pretend, right? You showed up. There we go. There's some enthusiasm. So we are starting a new unit here, latent trait models for binary responses. And for those of you who had a generalized modeling class with me or who had clustered multi-level models last year where we talked about generalized models, some of these slides will look very familiar. But I feel compelled to give you a place to start because I did not have this point of reference when I took IRT. So can I tell you a quick story? Start off with a story very, very briefly. So I took a class on item response theory, IRT, at the University of Kansas in I think the year 2000, so 20 years ago now, with Susan Embritson. So those of you who are in the IRT field know that she is a big damn deal. She literally wrote the book that we were using as the textbook for the course that had just come out. She's supposed to be working on a second edition that she's been working on for a good 15 years now. I'm not sure if that's ever going to be finished, but it's supposed to be. It's still on the list. I just found out last week. But anyway, um, I didn't know very much when I took this course about measurement. And so there were a lot of things that she said that I just sort of smiled and nodded. And I felt like, well, everyone else must know what this means, and I'd look stupid if I said anything. So I'm just going to keep smiling and nodding. And one of the things that she would say over and over again is that the model is linear in the logit. And the way she said it made me think it was a good thing to be linear in the logit. But I sat there the whole semester going, what the hell is a logit? Like, I don't know what you're talking about. No one's ever told me what a logit is, and I couldn't discern it from the context of what we were talking about. So I don't want any of you to wonder what the hell a logit is. Because if you don't know what a logit is, the rest of this is not going to make any sense. So we're going to start with that. What the hell is a logit? Why do we use them? And then the rest of IRT will make a lot more sense. All right, so away we go. And if you do have questions, don't sit there and nod and smile. Okay, learn from my mistakes. You can nod and smile, but then ask your questions in the chat window, or you can interrupt me because it's not an interruption. I want to hear from you. So please do not hesitate to ask questions. All right, so the big picture. So just a little bit of review where we've been relative to where we're going. So we started off with the world of classical test theory, the logic by which you can add items to create a sum score or a mean, and that's supposed to be the best estimate of someone's latent trait. So in that case, we can't separate out the properties of the items from the properties of the persons. For instance, if I have an item that's a binary item where only 10% of my sample gets it right, do I have dumb people or is that a really hard item? I don't know. They're tied together. And all of these, I'm going to say models, procedures for evaluating reliability in the context of classical test theory make assumptions about the model that underlies the data. So for instance, alpha assumes unidimensionality, it assumes items are equally discriminating, and it assumes that all of the items are independent after controlling for the factor. And what we just saw is that all of those assumptions are easily testable within a latent trait framework. And because we're not paying attention to the characteristics of the items, reliability is supposed to be greater to the extent that you have more items. So how do you make reliability better? You get more items. What kind of items? More. Doesn't matter what kind. What we just finished talking about is a particular type of latent trait measurement model. So the difference is that we're paying attention to each individual item response and the properties of the items and the properties of the people. So the sum of the items is no longer our best guess as to what someone's trait is. The trait is a latent variable in the model that's being used as a predictor. So the latent trait we called F for factor score, that's the predictor. The item responses are the outcomes. And as model parameters, each item gets its own intercept. That's our index of difficulty, which is conceptually backward because higher intercepts means higher means easier items. And each item also gets a factor loading, which is a slope, the change in the predicted item response for a 1 unit change in the factor, where higher slopes mean more discriminating items, items that have more of a signal to them than noise. And each item also gets an error variance for the amount of variability in the response due to not the factor, whatever that is. And so CFA provides a framework for testing hypotheses about the underlying dimensionality of the items. Do you think you have one factor or two factors? Well, that's a nested model comparison. You can see if adding basically a covariance between the two factors, allowing that to be less than 1, significantly improves the model fit, and if so, it looks like you've got two factors. Does each item actually contribute? So whether or not the loading is not only significant, but sizable from an effect size metric tells us whether or not each item is functioning the way we think it should. The catch with these models, though, is that we are assuming that the item responses are normally distributed and continuous. And that's rarely the case for most forms of items. Most of them are ordinal, and even if things are somewhat more continuous, it's unlikely that they're always going to be normal. A lot of times they'll be skewed, particularly for items that ask about extreme behaviors or extreme attitudes. But we did improve upon classical test theory estimates of reliability by adding omega. So omega is like alpha in that it assumes unidimensionality, but that's okay because our model would have already provided evidence for that. So if you have two factors instead of one, for instance, you need two omegas instead of one omega. It does not assume items are equally discriminating because the loadings go into the formula. And it does not assume that the errors are uncorrelated because any error covariances that you needed to add go into the formula in the denominator and they count against you if they're positive. But omega as an index of reliability of the sum score given the model still assumes that there's one value for reliability, right? Like I have an omega of 0.78, and that's supposed to hold for everybody. So in other words, if you have a set of items that are good, they're viewed as equally good for everybody without regard to whether or not someone has a high level of the trait or a low level of the trait. So in trying to increase your reliability, yeah, more items helps, but having more items with stronger loadings is what you're going for. So it's still more is better, but what kind of more has been refined somewhat to be items that have strong factor loadings. Measurement error is assumed constant across the trait. That's probably the biggest difference of the models that we're headed to next, is that that is not the case. The idea that if an item is good, it's not necessarily good for everybody is the biggest difference. And that corresponds to the fact that the models we're fitting are going to have a nonlinear relationship of the factor predicting the outcome, not a linear one as in CFA. Okay, so are we good so far?
You said so measurement errors in this case are not assumed to be the same across the trait.
In CFA,
I couldn't tell
are.
if you were saying that they are. Okay.
Yeah, where
Because I
we're
thought you said
headed
not in
next.
this case, so I wasn't sure. Thank you.
Yes, thank you for the clarification. Yes, in CFA, you get a number that is your reliability, and therefore you're assuming that that number holds no matter what your trait score. Said differently, you get the same standard error of measurement because that comes from the amount of error variance in your items, and it's constant across the trait. Where we're headed, it's not constant anymore. That's probably the biggest difference. So how does where we're headed relate to things you might already know? And this, by the way, is the biggest difference in how I learned item response theory, for instance, from Susan Emmertson, and how I'm choosing to teach it, is that IRT is nothing more than logistic regression with latent predictors. That to me makes a huge difference. I picked up generalized models when I was sitting in a class, auditing a class as a postdoc, and they started talking about logits, and I was like, oh, maybe I'm finally going to find out what the hell a logit is. And once I did, I was like, oh my God, this makes so much more sense now. So I feel like if you start with that framework in place, the rest of this makes so much more sense. So that's why I'm choosing to go about it from this way, with explicit connections to models that you've already learned. So for instance, if out of the context of measurement models for a few slides here, if you are trying to predict a continuous outcome variable, then you would do that within a family that's known as general linear models. That's ANOVA, regression, that kind of stuff. If you have observed predictors that are continuous, that are quantitative variables, that would be known as a linear regression, or a multiple linear regression if you have more than one predictor. And if the predictor is a latent trait, it's called a confirmatory factor analysis. But it's the exact same. You have intercepts, you have slopes, you have error variances, all of it works the same. If you are trying to predict outcomes that are not normal, then you switch from a general linear model to something that's called a generalized linear model. So special cases include logistic regression for binary outcomes, ordinal or multinomial regression for ordinal or nominal outcomes, Poisson regression or count regression for counts. Those are all special cases. And the big difference that we'll talk about in a minute here is that you're switching out the kind of distribution that goes with your residuals. If it's not normal, what else is it? And the other thing is that you have to pay attention to what the possible values of the outcome are to make sure that your model doesn't predict outcomes that go out of bounds. So the different models are designed to solve that problem of where does the line have to stop if you're going to have a slope. So in the same way that logistic regression, ordinal regression, and so forth has observed predictor variables, the families of item response theory models, IRT, and item factor analysis models are generalized models that have latent predictors. It's exactly the same. So we're going to start this process by reviewing basic concepts from generalized linear models as a backdrop for what we're going to have to understand in order to add the latent predictor part. So what the hell is a logit? That's first. So let me move. I just learned that I can move that thing out of my way. Hooray. The new thing of Zoom. And in addition to the video filters, it has a few more controls. So there's three parts to any generalized linear model. The first part is what's known as a link function. This is a transformation of the conditional mean to be predicted that makes it from something that has boundaries to a scale that has no boundaries. So the logit is one example. The probit is another example. The log is yet a third example. All of those things operate on the outcome to be predicted by the model, and it translates it from something that has a lower or upper boundary to something that's unbounded. So link function as a general concept. That's one part. The red part is the same linear model. Once you've translated your outcome into something that is continuous and unbounded, then you can have your regular old regression model just like normal. You can have your intercepts, you can have your slopes, you can have all that stuff. So at the end of the day, we're still going to have intercepts and slopes. They're just going to be predicting a different version of the outcome than the original. And then last, the conditional distribution. So after factoring in the contribution of the observed predictors, or the latent factors is where we're headed, what is the distribution for the data? And so if you have binary outcomes, for instance, it's Bernoulli. If you have ordinal outcomes, it's multinomial. If you have count outcomes, it's some kind of Poisson or negative binomial. Point being, there's all kinds of other distributions besides normal that are built into likelihood functions that we can use. So outcomes don't have to be any particular type. So let's start with binary. Binary is the easiest case, and everything that works for binary is also going to work for ordinal. As a special binary is a special case of ordinal. So let's say that we had a model. Just for a few slides here, I'm changing notation where let's focus on one outcome. So I have I as the index for person, like in regular old regression, and let's say we're going to predict one item's response from observed variables. So I have a model that might look like this. If I didn't know any better, I might go ahead and try to predict my binary outcome with a regular regression model. Questioned, so it transforms from categorical to continuous. Yes, that is what a link function does. So we'll see an example of that here in just a second. So what I'm actually trying to predict for binary data is the mean of a binary variable, which is the proportion of people who have a 1. So right off the bat, we're switching from the idea that the outcome variable can only have zeros or ones. The thing we're predicting, though, is the probability of a 1 for each person. That's the conditional mean to be predicted. So here's an example of a linear model we could use to predict that, where beta 0 would be the probability of a 1 when your x predictors are 0, and each of the slopes would be the change in the probability of a 1 for a unit change in x, and e is how far off your real answer is from the one that's predicted. So what could go wrong? Well, first off, probability has boundaries. So the model that I showed you here, these beta 1 and beta 2 slopes, these are linear. They say that the effect of x goes on forever and ever and ever, but it can't. So if we have a y-axis here that's the probability of a 1, then the model may go out of bounds at extreme levels of x. You can't have a probability of 1.2. You can't have a probability less than 0. So what we need is a way to tell the model, no, rather than this straight line, I want you to make this little bendy line, this S-shaped curve thing that asymptotes out as you get, it can't go above 1 and it can't go above 0.
Lisa?
Yeah.
Okay, can you go back to that?
Yes, love to.
So are you saying that if we were to use a general linear model, it would be the picture on, it's my left with the infinite?
The picture on the left with the question marks, yes.
Yes. And then when we use a generalized linear model,
Hmm.
um, what it does behind the scenes is switches it to this other form.
Yes.
Okay.
Yes. And
Okay.
so the behind the scenes is what I'm going to tell you about next. It's the magic of the logit as a link function.
That's helpful. Thank you.
Yes, thank you for asking. So yeah, the general linear model is shown on the left. And also shown on the left would be the analog of a CFA model, right? Where X is the latent trait. Same problem. A latent trait says that the slope is the change in Y for a 1 unit change in X. Well, there's no constraints on that. It keeps going and going and going, but we need the picture on the right. And the magic of the logit is that it's going to give us this picture on the right. So here's how this is going to work. The first step is to change the probability of a 1 as the conditional outcome to be predicted into something that's known as odds. And I'm going to get this right today. Some of you are giggling because I screwed this up so badly last spring, even before the pandemic. But that odds quantity is a ratio, but it is not the same thing as an odds ratio. Whoever made this terminology up should be drug out and shot. But if we take the probability of a 1 and divide it by the probability of a 0, that creates a term called odds. So odds has a distribution that starts at 0 and goes to positive infinity, where if the 1 is more likely, it's a value from 1 to positive infinity. And if 0 is more likely, it's a value that's shoved between 0 and 1. So it's a more continuous outcome than probability because we've gotten rid of the upper boundary, but we still have the lower boundary. And odds is weird. But if you take the log, the natural log of the odds, then you get to this wonderful thing called a logit. The logit is symmetric about 0, meaning where the probability is 50-50, and it goes on forever and ever in both directions. By the way, I say logit. Everyone I know says logit with the exception of a former graduate student. Shout out to Ryan Walters at the University of Creighton for this. He insists on saying that it's a logit because you log it, you don't log it. So I will accept logit or logit, your choice. But this is one of these things that you'll have to learn to commit to memory. The definition of a logit, I'm telling this to myself, the 20 years ago self sitting in IRT wondering what the hell is a logit? It's the log of the odds of the probability of a 1. I'll say that again with me. It is the log. I want to see your mouths move for reals. It is the log of the odds of the probability of a 1. Yes, that's what it means. So the logit is a nonlinear transformation of probability that takes the probability and turns it into something that is unbounded above and below. So here's a picture of the conversion where probability is on the y-axis and logits, our new best friend, is on the x-axis. So a logit of 0 corresponds to a probability of a 1 of 0.5. A logit of 2.2 corresponds to a probability of 0.9. So a positive value on a logit means a 1 is more likely than a 0. The opposite of that, so if I have a probability of a 1 of 0.9, that means I have a probability of a 0 of 0.1. So the logit of 2.2 becomes negative 2.2. So it's exactly symmetric. It's the same value whether you're talking about the probability of a 1 or the probability of a 0 with a difference in sign. So if I have a probability of a 1 of 0.99, which corresponds to a logit of 4.6, Can you guess what the probability of a 0.01 corresponds to in logits? Can you guess? Yeah, negative 4.6. Yeah. So this is super important to remember because in your output for some of these models, you will get parameters that are known as thresholds that correspond to the probability of a 0. And to turn them into intercepts, you have to multiply them by -1 to get the probability of a 1. So this concept will come back, but this is why logits are awesome. So question, would you be able to explain what the relationship between logit and logistic is? Logistic is the adjective that goes with logit. It comes from the idea that the variance of the logit comes from the use of a logistic distribution. The form of this curve that's shown here, the mapping of logits to probability, this is known as a logistic curve. So I think you can think of them as one and the same. Logistic curve is the adjective. Logit is what the scale is that is unbounded transformation of probability. So that's what the hell a logit is. It is a transformation of probability that takes the boundaries off. Here's another picture that I like that illustrates how this works. So equal distances in logits do not correspond to equal distances in probability. So on the top of this graph is probability, where 0.5 is the middle ground here. And on the bottom of this is the logit that corresponds to that probability. So a probability of 0.5 corresponds to a logit of 0. So if we go 1 unit in logits, if I'm translating from a logit of 0 to 1, that is a bigger jump in probability than if I am translating from, say, a logit of 2 to 3, corresponds to a much smaller jump in probability. Megan likes this picture. I'm glad you like this picture. I like it too. That's why I stole it from this textbook many, many moons ago. So in terms of each of these metrics, a probability of 50-50 corresponds to an odds of 0, which corresponds, or damn it, messed it up. Probability of 50-50 corresponds to an odds of 1, which corresponds to a logit of 0. There we go. That's what the middle is on each of these things. So logits allow us to have linear slopes that predict the logit of the response. So a 1 unit change in x can predict a logit that goes on forever and ever and ever. But when you back translate logits into probabilities, the corresponding probabilities shut off like they're supposed to. So question, does this mean we need to use all three in results and interpretation? In generalized modeling, yes. In this class, no. Odds are not used in IRT world very often, if at all. So we get to skip that one, which is just as well because I hate odds with a passion. But part of the disconnect for why, we'll get to this in just a second, but part of the disconnect for why IRT models look so weird relative to factor models is because they are written as predicting the probability directly, whereas factor models are written as predicting the logit directly. So a difference in what the outcome is part of the reason for the differences and why people get confused as to what these things mean. So this picture, going back to slide 7, this picture was made using an intercept of, let me see, a slope of 1 predicting the logit. So if you back translate logits to probability, then you get this S-shaped curve. That's how I actually made it. By factor model, do I mean CFA? Yes, CFA or IFA. CFA is written in predicting the logits when it's IFA models. So CFA for categorical data is IFA. IRT models are written predicting the probability. So they look like they're different, but you can rearrange them to get from one to another. So the logit solves the problem that the probability of a 1 has lower and upper boundaries. If we predict the logit of the probability instead, then we can have a regular slope for the effect of our factor just like we had before. So logits solve the boundary problem as the link function. The other part of it, though, is the residual. If you have binary outcomes, your residuals can never be normally distributed. Not only can they not be normal, they can't have constant variance, because the variance of a binary variable is not a separately estimated quantity. It's dictated by the mean. So if you think about a regression line, wait, this way? Is this correct for you guys? I'm always doing it backwards. Okay, if you think about a regression line where you're predicting the probability of a 1, if you have a predicted probability of 0.5, the people at that point where that's their predicted probability have a variance of 0.25. The people who have a predicted probability of 0.8, their variance is only going to be 0.16. So the use of a normal distribution to characterize the residuals that are left over can't work, because the normal distribution has only one variance that's supposed to be constant all the way along the regression line, and it's not a separately estimated quantity in binary data. It's determined from the mean. So we solved this problem for binary data by, rather than picking the normal that has separate parameters for mean and variance is supposed to be constant, by picking this thing that's called Bernoulli instead. And the function for Bernoulli is super simple. It's the probability of a 1, if that's what you got, times the probability of a 0, if that's what you got. So it's a very easy likelihood relative to the normal. So this is going to be the basis then of our height in the models to come for binary data, the height of each of the binary observations as a function of the Bernoulli. So here's what the model would look like then after we fix it. So rather than using a standard linear regression, general linear model to predict a binary outcome, what it would look like in what's known as a logistic regression, the use of a logit link function and a residual distribution that's Bernoulli. So if I start in logits, the log of the odds of the probability of a 1 as my outcome, then the model looks exactly the same as before. So beta 0 is still my intercept. The definition of an intercept is the expected outcome when your predictors are 0. Beta 0 is the expected logit when my x predictors are 0. Beta 1 is the slope for x1. It is the change in the logit for a 1-unit change in x. So in thinking about the outcome to be predicted, if you stick the word logit in front of it, then the regression model looks and functions exactly like it always has. Ta-da! So the logit version of this has the advantage of having slopes that are easily interpretable and have this nice additive property where it looks like a linear model of slope times variable plus slope times variable. But then you get to the y side and you're like, okay, but what the hell is a logit? Like if I told you my predicted logit is 2.1, is that good? Like what is that? And most people don't have an intuitive sense of what a 2.1 logit would mean unless you've been teaching this for many years. I can tell you it's above 0.5 because it's a positive number, but logit is not an interpretable metric. And if you make a picture for a presentation or a paper in which logit is the y-axis, someone's going to say, what the hell is this? What is a logit? Tell me what this means. So if you take the log off of it, if you unlog it, so to speak, or exponentiate as it's properly known, you can also write the model like this. And so if you unlog each of the coefficients, they become odds ratios instead of odds. I hate odds, and we don't have to deal with them in this class, so I'm not going to. If you unodds it, one more step down into probability, then that same equation looks like this. So now the pros of expressing it this way is that the left-hand side of the equals is the probability of a 1. That has a nice, like, people understand what that means. If I told my mom I have an 80% probability of not losing my mind today, she would know what that number means. But then what the hell do I do with this side? Right? I can't talk about these slopes in any kind of 1-unit change language because they're embedded in exponents. So to answer your question from several minutes ago, do we need logits, odds, and probabilities? Kinda, yeah. To interpret what the model parameters are saying, then that's easiest to do if they're predicting the logit, if we're up here. But to translate what a predicted logit actually implies, that's easiest to convey if you translate the predicted logit into probability. And so I made a table to try and help describe this translational process because this is super easy to get confused. So if I have a model that looks like this, I'm going to use y hat here as my predicted outcome. So the predicted logit given my linear model, that's the conditional mean to be predicted. The slope for x1 is readily described by the estimated slopes here in a logit metric. You can go from a logit to an odds, so you can convert the predicted logit outcome into an odds, and you can take that odds and convert it down to a probability as shown. So you can go from a predicted logit, say, of 2.1 to an odds of whatever the hell that is, down to a predicted probability of 0.86-ish, whatever it works out to be. The slopes, they talk about the change in logits for a 1-unit change in x. You can exponentiate them. You can take the log part off, and then that's an odds ratio, which is an effect size. And so negative slopes translate into an odds between 0 and 1. Positive slopes translate into an odds between 1 and positive infinity. That's why I don't like odds. But you cannot take an odds ratio and convert it down into the probability scale. You cannot unlogit a slope all the way down to probability because there is a nonlinear relationship between the two. So if I have a slope of 1, then that means that's the change in the logit for a 1-unit change in x. But to know what the corresponding change in probability is, I have to know where I am starting in logits. The slope of a change in logits has no direct analog to the slope of a change in probability. So all you can do is translate the predicted outcome into a predicted probability. So the logit is a new concept, but once we get our heads around what the hell this part is with the logit, IRT and IFA is a confirmatory factor analysis where you are predicting the logit of a response rather than the response directly. That's what it is. IRT looks different because the models are phrased in this probability way, predicting the probability directly, whereas models that are called item factor analysis, IFA, are written this way where you're predicting the logit. So they look different, but underneath the surface, they're all the same. Okay, how are we doing so far?
I have a question.
Please.
So I apologize for the people that are better at the math, but this is reminding me of like high school calculus and the area under the curve, and the way that the logit distribution looks like the area under the curve, like almost like a z-square would. I hope I'm not saying the wrong things here, but is that related?
Yes. I think you're thinking of the cumulative normal distribution function.
Yeah, exactly.
The one that goes up
Thanks.
to the top. Yeah. No, that could not have been a better segue into the next slide if I had tried. Yes. They are off by a factor of 1.7. So
Hmm.
this idea of a logit as an outcome variable, you will see people describe the same idea using a different set of terminology where they are using a model that predicts something called Y star. Have you seen this before, psychometric folks? No? Okay, well then this is new. Y star is described as the latent response. That is bullshit. Y star is a logit. It's not, it is observed. It's just, it's a nonlinear transformation of probability. And in models that have Y star as the outcome, they've added E back in. So you'll notice on all of these models on this page, there's no E residual anywhere. It's not because the models are perfect, it's because the E residual doesn't have an estimated variance. It's determined by the mean and it shifts as a function of what the mean is. If you see the E variance stuck in here, then what they're referring to is the idea that if we use the logistic distribution as what underlies this binary response, then that distribution has a variance of 3.29. So this number, by the way, will show up in a lot of places. It is the placeholder for residual variance if you are predicting in a logit metric. So since we don't have an estimated residual variance for the outcomes anymore, it's 3.29 in the logit scale, and it never goes down. It's always 3.29. So what you were talking about, Andrea, then, is the idea that there's another way that people solve the same boundary problem in binary data with a different link function that's known as a probit. So we have our friend logit and we have our friend probit. Do you remember intro stat where you had these tables in the back of the book where they had like the z-scores and there's like p-values inside the tables? Okay, that's what probit is. Probit is the z-score that goes with the area under the curve to the left. So z-scores have the same property as logits in that 0 corresponds to probability of 50-50. Z-scores go on forever and ever in both directions, so we can predict them with a linear slope, no problem, and not run out of bounds. And you need to use integration, math, to go back into what the probability is. But if you're in a probit link, then that corresponds to this idea of a Y star probit variance of 1 instead of 3.29. Does this matter? No. Here's the difference. If you believe in the idea of this underlying variable, what Y star is supposed to represent is the true outcome that underlies your binary response. So all you have are zeros and ones. But according to the model, what you actually have underneath that is some sort of continuous response that you've cut up. That's what the latent Y star is referring to. And these models say that that latent underlying continuous variable that gave rise to your observed binary response either has a logit shape to it, a logistic distribution that has a variance of 3.29, or it's probit that has a variance of 1. But here's the thing, folks. Do I know what the right answer is? No. Do I know what the pretend continuous underlying variable looks like that gave rise to my zeros and ones? No. Could I ever know that? No. It's all pretend. So this is just a way of setting a scale for the model that either corresponds to a logistic distribution or a normal distribution, logit versus probit. And someone figured out that these coefficients are off by a factor of about 1.7. So if you take the predicted probits, the z-scores, and you multiply them by 1.7, then you get the predicted logits. And do you see the difference between the red line and the black line here? Yeah, you gotta lean in for that one. Exactly. It's the same damn thing. So you will see logistic models more frequently because they're easier computationally. You can readily go from logits to odds to probabilities. To figure out what the p-value, the probability value is that corresponds to a probit, a z-score, you have to integrate, and nobody wants to do that. So someone figured out that the logit is a nice, handy computational shortcut. It's just on a different scale. So in IRT models, this idea of a probit link predicting the z-score that goes with that probability of a 1, that's known as an ogive, or a natural ogive, I think they call it. Although I've never seen an unnatural ogive, but maybe there is one. And the reason that I would tell you this is because depending on how you want to estimate your model for binary data, if you want to use full information maximum likelihood, you get to choose between logits and probits. They just differ in scale, doesn't matter otherwise. If you want to use limited information maximum or limited information estimation, you're stuck with probits. So I have to introduce both types of scaling. But either way, the job of the link, the logit or the probit, is to translate the probability into a metric that is continuous, unbounded, symmetric at 0, that we can then predict with a linear slope just like normal. And both of these options are symmetric. There are other types of models that make this curve asymmetric, known as log-log or complementary log-log. Those don't have an IRT analog, so we're not doing those here. Okay. So, questions? I know that's a lot of words, but the big picture, we're not predicting the binary data directly. We're predicting it indirectly. We're predicting the logit transformed version of the binary data so that we can predict it with a linear model the same as before. And rather than saying that the item responses have to be normal, we're saying that they have to be Bernoulli this week for binary data or multinomial in 2 weeks for ordinal data. So back to our regularly scheduled measurement class then, with that very brief background on generalized models. So how the models we're going to learn, item response theory / item factor analysis, IRT-IFA, are the same as CFA. They are the same in that they are for latent traits as predictors that are supposed to be continuous variables with a multivariate normal distribution in almost all cases. Instead of having an F for factor score, we're going to pick up a new word that's going to be theta, because these models use theta instead. The items are going to have separate item properties, so we're going to have difficulties and discriminations. We're not going to have error variances, though, because error variances are not possible for binary data. The same logic in testing unidimensionality is going to apply. So these models are going to say that after controlling for the trait, the item responses are independent, or after controlling for multiple traits if there's more than one. We can allow additional relationships between the item errors, but only through additional factors, method factors. So we'll talk about that later. The big difference is this idea of link functions being what's predicted. Rather than predicting the item response directly, we are predicting a nonlinear transformation of it that is continuous and unbounded. So IRT and IFA is the same thing as logistic or probit regression with a latent predictor. And the predictor has a new name. What used to be factor is now theta. So we'll add that to the list. The latent trait, latent variable, latent factor, latent construct, true score, factor is now theta. So for the next few weeks, factor is going to be theta. So here's the picture. Same exact ideas, changing the x-axis rather than to be an observed predictor to be an unobserved predictor, our latent trait theta. So if I have a factor model that is predicting the logit of the item response as my y-axis on the left here. So the log of the odds of the probability of a 1. That is what this y-axis represents. Then I can have a model that says the expected logit when theta equals 0 is 0. That corresponds to the probability of 50-50. The slope says that for every 1 unit change in theta, there is a 1 unit change in logit y. So the linear relationship between theta as my predictor, my latent variable, and the logit of the y. This is what Susan was talking about. It's linear in the logit. There is a linear relationship between the latent trait as the predictor and the binary item response as transformed into logits. So if I have a theta of 3, that corresponds to a logit of 3. If I have a theta of 4, that would correspond to a logit of 4, and that is fine because logits can go on forever and ever. But if I back translate logits into probabilities, so if I go from the link function, which is logit, to the inverse link, so I take the log off and I take the odds off, there is a ready equation to get from the y-axis in logits to the y-axis in probability. It's e to the logit over 1 plus e to the logit. You'll see this lots and lots. That nonlinear transformation puts the linear slope that's in logits into this logistic slope that predicts probability. The probability shuts off at 0 or 1. So a logit of, say, 3.5 corresponds very closely to a probability of 1, but not exactly. It'll be like 9999999 forever. So the model then predicts probabilities that stay within bounds, but it does so using a linear effective theta in predicting the logit of the item response. And if I wanted to swap out this y-axis for a probit instead, fine. It does the same thing. It takes probability and it stretches it out into something that is centered at 0 and unbounded. Just a difference in scale.
Lisa,
Yes.
the theta at the on the x-axis here,
Mhm.
is that, are those numbers meaningful?
Yes. Because we are going to set the scale of theta the exact same way that we set the scale of the factor. We're going to fix the mean to 0 and the variance of 1. So that this picture is showing plus or minus 3 standard deviations of the latent predictor.
Okay, and so those spots, or the points on the graph, are those, would those be like the factor loadings, or we would call them theta?
The points, so the slope of the line on the left is the factor loading.
Okay. Then what is on the right?
The right is what you get if you translate each of the points on the line on the left into a predicted probability instead of a predicted logit.
Okay, so they're just a transformation of the factor loadings.
A transformation of the predicted outcome.
Okay.
Yeah,
I think it makes sense.
Yeah, this is a very tricky concept because you cannot translate the slope. Because what happens is that the difference in logits does not correspond to the same difference in probability. So like if you look at the difference between, say, a theta of 2 and a theta of 3, right? That is a 1 unit difference in the predicted logit, but that translates into a like 0.1 difference in probability. Whereas if I did that same 1 unit difference in logits from, say, 0 to 1, that translates into a difference of like 0.2 in probability.
So basically what you're saying is you can't look at like one point on or one loading on the graph on the left and say it's transformed into this point on the right. You have to look at it as a whole. Is this?
You can look at one point, but it's not a loading. The points are the predicted outcomes from the model. So the result of a model that has an intercept of 0 and a slope of 1 for the latent predictor theta is creating each of these predicted points that the line is drawing through. So the slope of the line being 1 is like the factor loading. The result of applying that slope gives us each of these points on the y-axis in logits.
Okay, the points are logits, the slope is the loading.
Yes.
Okay, and then so the loading is transformed into this.
No.
Okay, I'm sorry.
I know it's very tricky. You cannot unlogit a slope. It's not the slope that's getting transformed, it is the result of the slope that is getting transformed. The predicted outcome is getting transformed. The slope only operates in linear space because of the logit.
Wait, okay, so I know I'm supposed to know this, but what is the predicted outcome then?
Okay. Yeah, that is actually a very good question because that's what makes these models so damn tricky is that there's 3 of them that you could potentially be referring to. In the data set, what I have is a column of zeros and ones. That's what I'm predicting, right? Whether someone has a 0, whether someone has a 1. So if I go back to just a model with no predictors in it, if I don't know anything else about a person, what's my best guess for their outcome? Well, it's the mean, right? That's the most likely number for any one person. What's the mean of a binary variable? Well, it's the proportion of ones. So right away, we're moving from predicting the zeros and ones in our data to the thing that is being predicted, the conditional mean, is the probability of a 1. That's the outcome, so to speak. The problem with predicting that probability ranging from 0 to 1 directly is that if we have a linear effect of a predictor, that linear effect of a predictor doesn't understand that y has to stop at 0 and at 1. So we can't directly predict the probability of a 1. So what we do instead is take that probability of a 1, divide it by the probability of a 0, that's odds, and then take the natural log of that thing. And that, the logit of the log of the odds of the probability of a 1, that is what the model is predicting. And because logits can go on forever and ever, we can have a linear slope of a predictor like normal. And the predicted logit is the y-axis on the left. But then to talk about that back in terms of our original data, we have to unlogit it. And the formula to unlogit is e to the logit over 1 plus e to the logit. That gets me to the y-axis in the picture of the right, which is in probability of a 1. The downside of looking at the picture on the right here is that I can't talk about this slope in the way that I normally talk about a slope. The slope on the right is not a 1 unit change in y, or it's change in y for a 1 unit change in x. It doesn't work. So we can't unlogit the line. What we unlogit are the y values in logits predicted by the line. And yes, this is hella confusing. So question, what is the role of a slope? Is it just showing the logit and the theta are a linear relationship? Yes. Yes. The logit, the purpose of a logit is so that we can fit a regular old linear regression model still. That is what a logit is for. It makes that possible because the logit gets back transformed into the metric that is bounded appropriately, probability in this case. Another question, so we can't go from a logit to a slope because the slope would not exist without a logit. The result of the slope is constant in logits. It is not constant in probability. Yeah. So if you want to talk about the slope as the change in y for a unit change in x, you can only talk about it that way if y is logit y or probit y. Because otherwise, let me go back to the equations. Maybe that will help. Going back to this slide here. So we're talking about the top line on slide 12 here, where I have a regular old linear regression model, and I can think of these slopes as the change in y for a unit change in x if I'm willing to say logit y. Then it all works out like we're used to. But if you take those same slopes to predict the probability with them, the expression looks like this, where the predicted logit is the term in parentheses. That's why I say that to go from logits to probability, it's e to the predicted logit over 1 plus e to the predicted logit. So I can't take these beta 1s and beta 2s in this expression and talk about them as the change in y for a 1 unit change in x. It doesn't work. That only works if I'm predicting logit y. So the role of the model is to predict logits or probits, but we can then back out of logits or probits to get the predicted responses in terms of probabilities. That's the order of operations.
So why and when would we want to do that?
We want to do that whenever we have an outcome where the conditional mean is bounded. So in this case, if I have a binary outcome, the conditional mean I'm trying to predict is the probability of a 1. That can't go past 0 or 1. Likewise, if the outcome I'm trying to predict is, say, a percentage, percent correct, rate of something happening, those can't go below 0 or 1 either. We use logits for those. If you're predicting a count variables can't be negative. The lowest count you can have is nothing. So then we need a link function that takes the linear slope and makes it so that it understands that it needs to shut off at 0. And turns out the natural log, the log of the count, does that very nicely. Because then the model predicts the log of the count using a linear slope. When you back translate that into counts, then it creates an exponential curve that asymptotes at 0, but keeps going on and on in the positive way. Okay. Does that help at all, folks who are asking questions? I've lost quite a few cameras. I know this stuff is hard. Can I just say that? But think of it this way, right? The biggest difference between the year 2000 when I was trying to learn this shit and 2020 when I'm trying to make you learn it, I didn't have the internet. I had a dial-up connection, and most of you probably don't even know what that means. But it means that I could answer like 1 email an hour. Like that was all I could do on my internet. It's not like I could ask the Google for help with any of this stuff, right? This is hard stuff. And even if you look for stuff on the Google about this, it's not going to be much more friendlier than what I'm trying to give you right here. But think of it this way. if this was material that you could just Google and in 10 minutes you'd have it with no problem, then this would be a giant waste of your time. You're in graduate school to be challenged, right? You're in graduate school maybe to get a degree so that you can get a good job, but hopefully a job that you can do meaningful work that challenges you intellectually, right? At least I know some of you are like thinking along those lines, like this shit is hard. It is. Like the only thing that makes it easier is repetition, because repetition leads to automaticity. So if you can commit certain definitions to memory, like what is a logit and why do we use it, then the rest of this gets a little bit easier. But if you've never seen this stuff before, then yeah, this is a lot and it's hella confusing. Um, it will make a little more sense once we get to IRT and IFA, but only uh, yes and no. In some ways it gets better and in some ways it gets worse. I'm not going to lie to you. But I will say that psychometrics is an area in which you can get a very good paying job coming out of graduate school. So if you can fight your way through this material to understand this stuff, there is potentially a reward there. And it's one of the areas of statistics that I think is least well covered for those of you who are here from other areas. Understanding this stuff will set you apart. And yeah, once you understand IRT and IFA, then you can do generalized linear models as well. Okay, so yes, back to your regularly scheduled measurement class. So terminology. This is actually a good place to leave this off because several of you had questions for me in your first homework when you're reading people's articles and trying to figure it out exactly what they did. So the reason why I'm lumping these two acronyms together, IRT and IFA, historically, these refer to different pairings of a particular type of way of expressing the model with a particular way of estimating it. So we're going to learn two different ways of talking about the exact same model. One of those ways is going to have parameters that are called difficulties and discriminations. Those of you who've taken IRT or measurement classes in this university will already be familiar with this. If you express your factor model predicting logits or probits in this way of talking about it that uses parameters of difficulties and discriminations that we're getting to next, and you estimate it with full information maximum likelihood, that combination of model form and model estimator is called item response theory, IRT. It's not a theory, but whatever. If you express the same idea of a factor model predicting logits using a factor model, so you have intercepts and slopes like we're used to, and you pair that version of the model with a different way of estimating it, what's known as a limited information estimator, that historically, that combination is referred to as item factor analysis. It is also called CFA for categorical data. So when you're reading these articles, if they start talking about CFA, keep reading. If in the description of CFA you see the words categorical data, or you refer to an estimation method known as WLSMV, or diagonally weighted least squares, anything that has the words least squares in it for that matter, that is IFA. It is not a CFA model. It's factor analysis on logits, rather than just factor analysis on the original responses. IRT is the same thing, just with a different way of writing the model that doesn't use slopes and intercepts. But I will show you algebraically they are equivalent. Oh, goodness. Okay. So this is where I want to leave off. You will see models expressed in predicting the logit. That's how IFA models tend to be written. And you will see models written instead predicting the probability, and that is how IRT models tend to be written. But these two are the exact same thing. The former, the logit, has the advantage of readily interpretable intercepts and slopes, but the disadvantage of what the hell is a logit that we're predicting. The latter has the advantage of probability as an outcome that people readily understand, but then the model itself is really hard to interpret in terms of what the parameters are doing. But they are the same thing. All right. This is hard for me too, guys. So I'll apologize if you see me closing my eyes when I start talking. It's not because I don't want to look at you. It's because I have to block out all stimuli to make sure that I say this shit correctly. It takes like all cylinders to get log of the odds of the probability of a 1 off the top of my head. So I'm not trying to block you out. I'm just trying to actually get this right. Okay, any last questions before we adjourn? All right, then if you haven't already done so, please do your next formative assessment before class so we can talk about that. Let me know if you need help with homework, CFA on your own data. Office hours start now. So peace out, guys.